Imagine having the power to predict the future, unlock hidden insights, and make informed decisions. Well, get ready to step into the world of linear regression, where we will unravel the secrets behind this incredible algorithm. Hey there, fellow learners. Welcome back to my channel. I am Bhaskar, and today we are embarking on the exciting journey into the fascinating realm of linear regression. In this video, we will demystify this fundamental algorithm in machine learning and explore how it can empower you to uncover valuable patterns and make accurate predictions. Linear regression is like having a trusted guide that helps us model relationships between variables. It's a crucial tool in various fields from finance, marketing to healthcare and beyond. So, are you ready to unlock its potential? Let's dive in. Understanding linear regression. Yes, before we jump into the mathematics, let's start by understanding the core principles of linear regression. Trust me, it will make the journey much smoother. In section 1, we will unravel the essence of linear regression. We will explore its definition, its goal of modeling relationships between variables, and how it brings order to the data chaos. Linear regression is all about finding the best fitting line that represents the relationship between variables. It's like finding the thread that weaves the story of our data together. But hold on, before we dive into details, we need to understand the assumptions underlying the linear regression. These assumptions act as a guiding principles, ensuring the accuracy and reliability of our models. Linear regression makes several key assumptions to ensure the accuracy and reliability of the model. The assumptions are important to consider when applying linear regression to the real world data. Let's explore the main assumptions of the linear regression. Before the assumptions, let me take you uh, through this example. Yes, so the linear regression is nothing but a straight line in simple terms. For example, y equal to mx plus c. It's just a straight line. That means if you draw a graph, it's this line, or you consider this line. Okay. So in simple terms, linear regression, if you have independent variable and dependent variable. So y-axis is our dependent variable and x-axis is our independent variable. So if we have data points like these points, these are our data points. And if you plot a line through it, that's our linear regression. So, so these points are our independent variables. These are our data points. These points are data points. So now let's go to the assumptions of linear regression. First assumption, linearity. The relationship between independent variables or features and dependent variable or target should be linear. That means y equal to mx plus c. This is what it signifies. The x is independent variable, y is dependent variable, and this relationship is linear. Next assumption, independence. The data points or observations used in linear regression should be independent of each other. That means this data point is independent of this data point. This data point is independent of this data point. Okay? Yes. In other words, there should be no dependence between the observation. Violating these assumptions can lead to the biased and unreliable results. Next assumption, homoscedasticity. Homoscedasticity assumes that the variance of errors or residuals is constant across all the levels of the independent variables. This means that the spread of residuals should be consistent as the values of independent variable changes. So let's take an example. Homoscedasticity. So if you plot the plot, so if I take two these data points, and this is our linear regression line, or the best fit line. So this is this variance should be this one. Okay, the variance should be equal, kind of. Okay, next one. Heteroscedasticity is present. It indicates that variability of the errors changes, leading to potential issues in the model predictions. Next assumption, normality. The error terms or residuals should be normally distributed. This assumption assumes that the distribution of errors follow a bell-shaped curve around zero. The deviation from normality may suggest the presence of outliers, inferential points, or mismatch between the assumed and actual data distribution. That means these are our errors, right? So if you plot a plot between the errors, it should be normally distributed. So the error should follow normal distribution. Okay. Next, no multicollinearity. Okay. So multicollinearity occurs when there is a high correlation between the two or more independent variables in the regression model. This can make it difficult to determine the individual effects of each variable or the dependent variable. Detecting and addressing the multicollinearity is important to ensure the stability and interpretability of the model's coefficients. So, what is multicollinearity? Multicollinearity assumes that there is high correlation between two or independent variables. Let's take an example. Y equal to m1x plus m2 x2. So x1 and x2 are independent variables. There should be no relationship between x1 and x2. What does it mean? Let's take x1 equal to 1, 2, 3. These are the values of x1. What about x2? Let's take x2 equal to 2, 4, 6. x2. So is x1 and x2 dependent on each other? Well, exactly, because x2 equal to 2x1, right? That means it's violating the assumption of multicollinearity. There's a dependence between independent variables. So we should not have multicollinearity. Okay. Let's go to next assumption. No endogeneity. Endogeneity refers to a situation where there is a bidirectional relationship between the independent variables and the error term. This violates the assumption that independent variables are exogenous, meaning they are not affected by error term. Endogeneity can lead to bias and inefficient coefficient estimates. So, what is endogeneity? There should be no bidirectional relationship between independent variables and error term. That means if you take our y equal to mx plus c between the x and the error term, okay, error. So, what is error? Error is nothing but actual minus predicted, y minus y cap whole square. So we will come to it in later. Okay. So between error term and ex, there should be no relationship. Okay. So it is essential to check these assumptions before interpreting the results of linear regression model. Violation of these assumptions may require additional steps such as data transformation, variable selection, or selecting alternate models. Okay, in this section, we will journey into the world of simple linear regression and multiple linear regression. We will explore how these variations allow us to model different scenarios and uncover deeper insights. Okay, next. mathematical foundations of linear regression. Now that we have our solid understanding of linear regression's essence, let's uncover the mathematics that powers this algorithm. Don't worry, I will be your guide through the numerical wildness. So, in session 2, we will explore the mathematical foundations of linear regression. We'll dive into the methodology behind the screens to demystify the magic. Linear regression relies on the extraordinary power of ordinary least squares matter to find the optimal line. To bring our equation to life, we will calculate the coefficients, slope, intercept using least squares approach. But remember, it's not just about numbers. We need to interpret and understand how these coefficients tell compelling stories about our data. So, what is simple regression? Well, let's find out. Y equal to mx plus c. This is the simple regression. So linear regression is a straight line, passing a line through the center of observations. That means, so if these are observations, you should see a central line or the best fit line. Okay, and what is the error? Well, you already know. It's a difference between the data point and predicted data point. Okay, so now let's dive into the multiple linear regression. Let's take example y equal to m1 x1 plus m2 x2. It's a multiple linear regression. Why is it multiple linear regression? Because we have more variables x1 and x2. What about y equal to m1 x1 square plus m2 x2 square? Let's take it just cube plus m3 x3. So is it a linear regression? You are having square, cube root, and 1. Yes, it's a linear regression. Why is it linear regression? Because it is linear in terms of coefficients m1, m2, m3. It's not about the independent variable. It's all about the coefficients. Okay, I hope it's clear. So this is the multiple linear regression. Okay, to ensure the quality of our models, we will explore evaluation metrics like R squared and mean squared error. This matrix acts as our compass, helping us navigate the vast landscape of model performance. What is MSE? Mean of, square of, errors. So what's the error? Y minus y cap. So take a square. I'll take a mean. This is our mean square error. Okay? Yes. Next, there is one more matrix which we commonly use for linear regression. That is R square. R square is a statistical measure commonly used in linear regression to evaluate the goodness of fit of your regression model. It provides an indication of how well independent variables explain the variability of dependent variables in the model. So, what is R square? R square is a matrix which explains the variability of independent variables by a dependent variable variability. R square is a value between 0 and 1, with 0 indicating that model does not explain any variability in the target variable, and 1 indicating that model perfectly explains all the variability. Here's a detailed explanation of R square in the context of linear regression. R squared measures the proportion of variance in the dependent variable that is predictable from the independent variables. In other words, it quantifies the percentage of variability in the target variable that can be attributed to the independent variables included in the model. So let's go to equation. R square, yes, R square equal to 1 minus SS R by SS T. This is our R square matrix where SSR is sum of squared residuals. What is it? It is sum of square differences between the actual target variable and the predicted values obtained from the regression model. What is SST? It is sum of squares total. This is nothing but sum of square differences between the actual and mean of target variable. So let's take example. SSR. This is the sum of squared error between actual and predicted. SST. Sum of squared error between the actual and mean. Okay. I hope it's clear now. R square ranges between 0 to 1, but it also takes negative values if model performs worse than simple horizontal line or Bayesian model. A negative R square suggests that model is not capturing the underlying pattern in the data. So, what is the conclusion? R square is a measure of how well the independent variables explain the variation in the dependent variable in the regression model. Okay, higher R square indicates a better fit, but it should be interpreted in the conjunction with other evaluation metrics. Okay, let's go to the session 3 example application of linear regression. Okay, now that we have solid foundation, it's time to put our knowledge into action. Okay, the example we are going to take is we'll step into the world of predicting the housing price and witness how linear regression transforms the data into powerful insights. We can predict the housing price. Y is our price, X can be. What is Y? Y is a dependent variable. So we want to predict the housing price. Okay, so what do we need? We need independent variables. What are our independent variables? What can be? Let's think. It can be area location, distance from popular hotspots, number of rooms, size of the house, that's how many square feet. So, so we have our independent variables, we have our dependent variables, y equal to mr x1 plus m2 x2 plus m3 x3 plus some other variables plus a constant or intercept. This intercept is also called bias. Okay, good. So this can be, for our example, this can be our number of rooms, area location, size of the house, and more. Okay, congratulations on completing this fantastic journey into the world of linear regression. We covered a lot, and I hope you are as excited as I am about the power and versatility of this algorithm. Now it's your turn to unleash your creativity and apply your newfound knowledge. Remember, linear regression is just the beginning of an incredible machine learning journey. Make sure to collect out other videos in Machine Learning Mastery playlist for more advanced algorithms and techniques. Together we will conquer this world of data. Before we part our ways, I have a small request for you. If you enjoyed this video and found it valuable, please show your support by liking, subscribing, and sharing it with fellow learners. Thank you for joining me today and investing your time and enthusiasm in exploring the captivating world of machine learning. Keep nurturing your passion for learning and remember the possibilities are endless in this ever evolving field. Until the next time, happy learning. Thank you.